Here is the translation of your presentation script into technical English. I have organized it by slide as requested.
Good morning. We are the group number 5, composed of myself, Santiago Rosales, and Oliverio Los Rios. Today, we are pleased to present our final project, the design and implementation of a functional point of sale terminal based on RFID technology. Over the next few minutes, we will how we build a complete system ranging from embedded hardware to a desktop management application.
To organize our presentation, we'll follow this outline. First, we will provide general introduction to the project and perform a live demonstration so you can see the system in action. Then we will delve into the hardware architecture we designed and the key components we utilized. Next, we will analyze the three communication protocols used in our system: SPI, I2C, and UART. Afterward, we will explain the logic behind the software, both the firmware running on the microcontrollers and the desktop application in Python. And finally, we will share our conclusions and the main lessons we learned from this project. The goal of this project was to create a complete contactless payment ecosystem. We wanted to simulate the entire flow of a real transaction, from the hardware interacting with the user to the software managing the data. To achieve this, we implemented a distributed processing architecture. At the center, we have the Arduino Nano, acting as the main brain. It handles reading the RFID card, controlling actuators like the relay and buzzer, and fundamentally communicating with the PC application.
The Arduino delegates a very specific task, screen control. A PIC 16F8778 microcontroller functions as a slave coprocessor. Its sole job is to receive via the E2C protocol and display it on the LCD. Finally, the entire system connects via USB to a Python application which manages the user unbalanced database. This application makes the logical decisions such as improving or rejecting a payment. Now, to see how this all works together, we are going to perform a demonstration. As you can see on the LCD, the system is in standby, indicating approximate tarjeta tap card. Now I'm going to tap a card that is registered in our database and has sufficient balance. Sir, the LCD shows the card is being read. The Arduino sends the UID to the PC. The Python application validates the payment and returns the information immediately. We can hear the success buzzer. The relay activates, simulating, for example, a door-style opening, and the LCD shows as the divided amount of and the new balance. On the computer screen, we can see the transaction has also been reflected. Next, I'll reduce a second card that is registered but has insufficient balance for the payment.
¿Es eso?
Again, the system reads the card. For this time, the PC application rejects the transaction. As a result, we hear the error sound and the LCD shows saldo insuficiente, insufficient balance, and most importantly, the relay does not activate.
¿Es eso?
Este va segundo. Finally, what's happened if the card is not on the system in the system? The system reads it, but the database does not recognize it. Again, we receive a visual and auditory error notification on the LCD. Tarjeta no registrada, card not registered. The PC interface allows us to register this new card if we want to. Now, let's analyze the key decision of our architecture. The use of two microcontrollers. As the main control unit, we choose the Arduino Nano board. It's at Mega 328B microcontroller operating at 16 MHz. Is more than capable of acting as the system master. The main reason for this choice was its development ecosystem. Deliveries for SPI serial and especially for the MFRC522 model are highly developed and tested. This allows us to focus on high-level logic rather than reinventing low-level communication.
For the visualization task, we selected the PIC16F877A. In our design, this powerful microcontroller acts as a slave coprocessor. Its sole and exclusive function is to receive commands via I2C and manage the LCD 4-bit interface. Why do this? Because controlling an HD44780 LCD requires precise timing and takes up several pins. By delegating this task to the PIC, the Arduino code remains clean, focused on business logic, and we guarantee that the screen updates independently, without interfering with critical earth reading. In short, it is a classic division of labor in embedded systems. One processor for application logic and another for peripheral control.
Se fue el clic por atrás. The hardware ecosystem is complemented by these four peripheral components. First, the 16 times 2 LCD screen. It is our main user interface. It is based on the standard HD44780 controller, and we drive it in 4-bit mode from the PIC to optimize pin uses.
For physical interaction, we use a one-channel relay model. It is an electromechanic switch that allows us to control an external power circuit with a small digital signal from the Arduino. In our case, it simulates the opening of a barrier. It is important to note that it is active low, meaning it activates when sent a logical 0.
Next, an active buzzer. Like a passive buzzer, this one has an internal oscillator. It simply needs to receive 5 volts to emit a note, a tone, making it very easy to control to generate success or error sounds alerts.
And finally, the RFID RC522 module. This is our near-field transceiver. It operates at 14.34 MHz and is responsible for generating the electromagnetic field to power the passive card, send request commands, and receive the ACK. All communication with this module, as we mentioned it, is done by SPI. Our distributed system depends on the correct implementation of three key communication protocols. Each was chosen for a specific reason.
First, SPA. We use it for communication between the Arduino and the RFID module. The main advantage of SPA is its high speed and full duplex design, allowing for very fast and efficient data exchange. It is fundamental for MIFARE protocols and protocol operation, which require sending commands and receiving responses with specific timings. On this line, the Arduino is the master and generates the clock signal. In
Second,
data
I
streams.
square C. This is the bus that connects our two microcontrollers. The greatest advantage is hardware simplicity. Just two wires, SCI and SCC, plus two pull-ups resistors to connect multiple devices. In our case, the Arduino, as master, sends data frames containing the text to be displayed, and the PIC, as slave, listens at its address 0x21 and processes the data. It is the ideal solution for low to medium speed peripheral control on the same board. Such as the UID card or serial communication.
This is the
UID
protocol
to the
that
PC
connects our hardware
and
with
the
the PC application to the Arduino. We use the Arduino native
the USB
indispensable
connection.
bridge, which create a virtual COM port. It's an asynchronous point-to-point protocol, perfect for transmitting data streams, such as the UID card to the UID to the PC and phones back to the Arduino. It is the indispensable bridge. These three protocols working together allow us to have a modular and efficient architecture.
Now, let's delve into the software implementation, analyzing the logic behind the firmware that brings our hardware to life. We'll start with System Brain, the Arduino Nano. This is the firmware running on the Arduino. We have structured it into three main parts: configuration, main loop, and support functions. At the beginning, we define all the pins we are going to use. This is crucial for organization. Note that the relay pin is relayed as relay on with a low value, because this module is active low. Do you understand this? Thank you. We also define the peaks I2C addresses. Here, you can see it. In the setup function, if we scroll, SPI begin, and mfr22. The functions initialize the SPI hardware and send configuration commands to the MFR to activate the antenna. Software I2C configuration. Here we simply configure the SSL pin as output and set it high. We send welcome message to the LCD and execute the startup sound sequence. P. The loop is the heart of the logic. It functions as a polling cycle. MFR22 peak sends an RF request RECA to check for cards. Returns true if one responds. And sorry, MFR22 peak read card serial executes anti-collision loop to select a card and retrieves its UID. Serial read string until here you can see this is a blocking instruction with a timeout. The Arduino waits up to 3 seconds for a response from Python. Response analysis and activation. We analyze the response to determine success. A flag was successful or controls the relay. This ensures the relay only activates after back-end validation. Digital write. We can see this here. And LMFR22 pick halt A. Finally, we send a halt command to the card to put it in an active state. Here we can see approximate target. This means
Now let's look at the receive code. The PIC 16F8778. This firmware writing CCSC is much more direct. At the top, we have the configuration fuses HC of our 20 megahertz crystal and no LVP and HC of our 20 megahertz crystal and no LVP to disable low voltage program. The most important directive is use E squared C slave address 0x42. This configures the big MSSP hardware module to the function in 7 bits slave mode, responding to the address 0x21, which is 0x42 in 8-bit format. The main is very simple. After initializing the LCD, we enter an infinite while true loop. And this line This is the key instruction. The program stop here, conserving energy. The MSSP hardware monitors the bus. Only when detects a start condition followed by its known address does E square C poll return true. Read loop once activate the pig enters a do while loop to read the frame. Comic byte equals C2 C read 1 read the bit from the SSP buff and sends an ACK. Stream processing. Once the string is received, terminate by 0 with the string switch to find the comma. If found, we replace it with a null terminator, splitting the buffer. When then print the first part on line 1 and the second part of line 2 using LCD go doxy. If comma no exists, everything prints on line 1. As you can see, the pig makes no decisions. It's a highly specialized peripheral converting E squared C commands into LCD actions. Finally, we arrive at the last piece of the ecosystem, the desktop application, programmed in Python.
This application is a true backend of the system. While the hardware handles
Next,
physical integration, this is where the business logic resides. To build it, we use several key libraries.
this application is a true backend of the system, while the hardware handles specific. This application is a true backend of the system, while the hardware handles physical interaction. This is where all the business logic resides. To build it, we use several key libraries.
tkinter, the standard Python library for creating graphical interfaces. We use it to design this window that allows the operator to manage the system intuitively. Isn't it beautiful? PySerial, fundamental for communication. It runs on a background thread to constantly listen to the serial port. This prevents the graphical interface from freezing while waiting for data from the Arduino, ensuring the application remains responsive. SQLite, our database engine, it is a simple file on the hard drive that persistently restores each card's information, UID, holder names, and balance. When a UID arrives from the Arduino, the application queries this database to make a decision.
An OpenPixel, which allows us to write Excel files every time a transaction occurs where access is failure or registration. The application automatically logs it, creating a permanent and auditable record.
In summary, the Python application centralizes system intelligence, manages data, and provides a complete control interface.
To conclude, this project has been highly cultivating integration experience. The main achievement was the successful implementation of a distributed processing architecture. We validate that splitting tasks between a main processor for logic and a coprocessor for peripheral tasks is a correct and effective approach. We learn in practice to debug and make communication work between different platforms. That was the case with E2C between the Arduino and the PIC.
We successfully integrated three different communication protocols, SPI to C and WART, making each fulfill its function optimally within the ecosystem. Furthermore, the project gave us a complete view of project development, ranging from low-level framework in C through a high-level framework in the Arduino framework to a multi-threaded desktop application with database and report generation. Finally, the challenges we faced, such as the need to implement software I2C or managing the currency in Python, were the most valuable learning opportunities as they forced us to seek robust technical solutions that should go beyond theory.
Okay, thanks for watching. This is the project to Gabriel Gunther Martinez Mamani in digital techniques in fifth year to the
This teacher allowed us to push the limits of the PIC 16. Now,
okay,
the sources: microchip PIC 16 F87XA datasheet DS39582B includes a specification of the PIC 16 F877A microcontroller, such as architecture, memory organization, peripherals, MSSP, USART, registers, and electrical characteristics.
NXP MFRC 522 contactless reader IC datasheet Web 3.4 details the operation of the RFID reader and write IC, its operating modes, the communication protocols it supports, ISO EEC 14443A, description of its internal registers, and the SPI interface.
Crystal fonts CFAH1602A HB shape datasheet specifies the characteristic of the 16 by 2 module LCD, including its dimensions, optical and electrical parameters, pinout, and the instruction set of the HDD HD44780 compatible controller.
The Titron LM7833 and LM7847 1 ampere positive voltage regulator datasheet describe the voltage regulator used to adapt the power supply for the RFID module, detailing its electrical characteristics, package, and typical application circuit.
Actually, we didn't implement this positive voltage regulator, but we did research it, and it was a main part of the project.
Okay,
We are Santiago Rosales and me, Oliverio de los Ríos. Now we will make some acknowledgements to our
wait. Jean-Paul Rosemary,
Gabriel
Gabriel
Gunther
Gunther Martinez,
Martinez,
Gemini 2.5 Pro, and 3.
Tiziano Arrieta,
Alexander Müller,
Leandro Bonet,
Norbert Baigorria,
Maria Cecilia Secocci,
Gottfried,
Gaston Sebastian Bergesio,
Alexander Müller,
Ezekiel Marjorie,
Janek Anthony Fuchs.
These people made the project possible. Without Cuthbert, that is one of the members of Embedded Engineering Discord, we wouldn't have known about the possibility of level shifters that actually we didn't use.
Okay.
Goodbye.